Welcome to the parallel session from Nick Murray. Very excited to have Nick here. And we will be beginning soon. I think we're just waiting for more people to join us. So Nick, how was your workshop in the morning?
Oh, really good. Yeah, really good.
Was it the same talk?
What's that?
Was it the same talk, the one that you're giving now?
No, it was an interactive workshop actually with about 45 Australian scientists working on ecosystem health across Australia. So that's good. Yep, so ready to go for another one.
Nice. So that's like across different ecosystems, not just like the intertidal. Right?
It is, yeah. We're working particularly in national parks, trying to understand risks to ecosystems and how to best manage them.
Yeah, I can imagine this is an issue, especially the fires that happened in 2019, and they want to monitor the changes.
Yeah, exactly, and try to get a larger scale understanding than a sort of national park by national park assessment of how ecosystems are changing. So we're working at the much larger level than what most environmental management is done in Australia.
That's cool. Thanks. Real great jumping from one workshop to another. So I guess we have more or less, stabilized in terms of increase in numbers. But, we could probably begin, and then so, we can get on with this really exciting talk. So apologies for me just sharing the browser. I'm not very good with Zoom, so I'm just going to show you some welcome slides from my end. So welcome to everyone from our previous workshop from Nick Clinton. Now we're moving to this specific workshop from Nick Murray. And he's going to talk about losses and gains of Earth's intertidal ecosystems, which is a really interesting and very challenging ecosystem to map. So this is definitely something that's really interesting and definitely will provide more insights on how to use EarthEngine. So I'll be introducing Nick. Nick recently moved to James Cook University. He's a senior research fellow and ARC DECRA fellow in the College of Science and Engineering in Townsville. Nick's research spans the fields of remote sensing, conservation biology, and ecology, and he uses spatial models to investigate the dynamics and status of coastal and terrestrial ecosystems. Nick's work has been recognized by several awards, including the 2016 IUCN Commission on Ecosystem Management Emerging Scientist Award, Australia's nomination for the Apex Science Prize, and the 2015 Eureka Prize for Environmental Research as part of the IUCN Rate List of Ecosystems Science Team. I met Nick, I think in 2013 or 2014 in Bangalore for the Society of Conservation Biology program conference, and was really wowed by his presentation. He also gave a really wonderful talk at the 2017 Google EarthEngine User Summit, and I'm sure most of you would be familiar with his paper looking at the intertidal mapping across the world. So before I pass the call to Nick, once again, I also like to inform the audience of two things. Firstly, that this talk is recorded. So this is something that Nick Puccino will be helping me with recording this talk. And secondly, we will be using Slido for our Q&A session. So just go to the website and type in EarthEngine SG1 in the participant code, and you would find, I will probably post the link also on the chat group. So I think with that, I will stop share, and I think, Nick, you could probably try to share your screen.
Sure. Tell me if you can see this.
Yeah, I can see it.
Great. Okay, well, I'll get started straight away. Thanks, Janice, for the invite, and thanks to Nick for managing the technical aspects of this. It's really appreciated. And yeah, really nice to join this really incredible initiative to help sort of spread the use of Google EarthEngine around the world. It's such a useful tool, and as someone who's been using it since about 2013, I think it's really nice to join a meeting like this and introduce some of the really large scale ecological questions we've been able to answer and that we're trying to answer using Google's research infrastructure. And today I'm going to be talking about a new project that builds on some of the work I've published previously on tidal mudflats to understand how the world's intertidal ecosystems are changing with global change, such as coastal development, and also climate change. So first up, this is Tokyo Bay in Japan. And the thing to notice here is just that all of the natural coastal ecosystems have been heavily impacted by urban growth and infrastructure development around the bay. This type of story has happened worldwide with the rapid growth of human populations in coastal regions. And the question has begun to be, well, just how much have the coastlines changed in response to these types of fine-scale changes? And if possible, can we get an understanding at the global level? So a few years ago, 2016, I was lucky enough to be funded by the Google EarthEngine Research Award program, which was a research grants system at the time to really test EarthEngine and find bugs in it and develop some complex analyses that would really stretch EarthEngine to the limit. And I worked with Nick Clinton, who I know you've all been listening to for the last hour, Nick Clinton and a couple of other Google EarthEngine developers, as well as scientists at the University of Queensland and University of New South Wales to make a map of tidal mudflats. Now, we called this at the time a Google scale problem. Understanding the distribution of an intertidal ecosystem such as mudflats, which fringe the coastlines of most of Asia and much of the rest of the world, required the ability to interrogate every single Landsat image that we could possibly get our hands on. We needed to be able to identify images that were collected at low tide and high tide and build a classification system that could be parallelized for global scale investigations. And I first met the Google team in San Francisco and discussed this problem with them. Before this, I'd been able to make maps of mudflats around China and Korea, but I would spend 3 or 4 months at a time downloading Landsat images. And we went to Google with this issue that we really wanted access to all of the Landsat archive to identify pixels which are inundated at high tide but exposed at low tide, and developed a classification system that could do that in EarthEngine. We ended up doing it as a time series. The time series was 11 time steps since 1984 to make a map of tidal mudflats. We were able to use information from more than 700,000 Landsat images, and we developed a machine learning pipeline essentially based on training data to classify more than 30 billion pixels for one time step. So this was a computation that was just impossible for us to ever be able to achieve on research infrastructure here in Australia. We achieved it. We've made the data publicly available on intertidal.app, and you can access it through Google EarthEngine as well. And what it looks like is a data set such as this. So this is cycling through the distribution of tidal mudflats in South Korea over those 11 time steps starting in 1984. And each color represents a different time step in the time series. And so if I pause it and highlight how you might read this information, what we have here is tidal mudflats, the extent of tidal mudflats that we detected with the classification of Landsat imagery. And the color yellow represents the last time step in the time series. That's 2016. So the distribution of tidal flats in the year 2016. Now these purple areas were what we detected as tidal flats earlier in the time series. And so where you get these large areas of purple, such as along the coast here, this is Seoul over here. And this here suggests that a very large area of tidal flats have been lost in that 30-year period. And when we go into these areas on the Earth's surface and see what they are, in this case, it's Incheon Airport. Many of us have been there. It's built entirely on what was formerly a tidal mudflat ecosystem. So we can see this all around the world. We're able to detect just the amount of impact that coastal infrastructure like this has on intertidal ecosystems. And this airport, the 4th most expensive airport ever built, was built entirely on tidal mudflats, mainly because it's an extremely flat area. It's not owned by anyone. And so governments are able to develop these sorts of developments on tidal mudflats, and it's had an enormous impact on this important coastal ecosystem globally. So we ended up publishing this analysis in Nature, and we've made the data publicly available. It's getting fairly widely used, and sort of most importantly and most pleasingly, this EarthEngine analysis that was just not possible before we were able to use EarthEngine. We first showed that tidal mudflats, this ecosystem that's common in Asia but not so common in other parts of the world, has a global extent that is probably a bit larger than mangroves. So we kind of call it an overlooked coastal ecosystem, even though it fringes sort of many of the world's mega cities, and it's dynamic. It offers a bunch of ecosystem services that are important to coastal communities. It was overlooked because of this remote sensing issue of just not being able to get enough data to find the low tide images that allow us to map the ecosystem. Since that time, since this rapid loss of this ecosystem for things like airports and port developments, particularly in Asia, but also in South America and Africa as well, there's been a lot of conservation work on this. So putting an ecosystem like this on the map has really been a basis for some conservation, such as the World Heritage listing of tidal flat sites. We've used this data, and other organisations have used these data to determine the edge of national parks in coastal regions to make sure they completely cover this intertidal ecosystem. And the data set itself was selected as one of the headline indicators that could be used for assessing global conservation targets over the next 10 years. So some really nice outcomes, and just really, really pleasing to put this, what I think is an incredible ecosystem on the map and make the data publicly available. All of the EarthEngine code for running it is also made publicly available. And we took the classification pipeline, which is essentially just a random forest classification of Landsat data based on a training set, and generalized it with another Google EarthEngine Research Award into our app, which is called Remap, which is essentially a front end to Google EarthEngine before EarthEngine had sort of the advanced mapping features that they've got now. So you can go to that app and you can use the exact same classification framework that we use for this data set. We also adapted it to mapping the terrestrial ecosystems of Myanmar and made a map of 64 of Myanmar's terrestrial ecosystems, also publicly available at the website on this slide. Now, this takes me to the second step of this talk. So the first half was about what we've done and what we've published. And now I want to take you into some of the sort of really important science questions that analysis sort of revealed to us and allowed us to dive in even deeper using EarthEngine to really try to understand the global dynamics of intertidal ecosystems. Now, some of the important findings we made in that project was that there was a decline of tidal flats, and that's understandable given those really observable impacts of coastal reclamation for things like airports and port developments. Also sea level rise, sediment compaction, all of these drivers are known to be impacting the extent of tidal flats. However, over the last 15 years, we found that it wasn't a significant decline. So it wasn't as big as we were really expecting, having traveled the world's coastlines and seen the sorts of threats that you have to this ecosystem. And once we started looking into this question of, well, it's not really as big as we would think in the last 15 years, what's going on here? We discovered a number of really interesting things. One is that tidal flat losses were often to other coastal ecosystems. So often you would detect an extent reduction of tidal flats, but at the same time you could observe mangroves extending onto tidal flats. This sort of dynamic is observable in delta regions, in India, Malaysia, southern China as well. We see that the sort of impacts of tidal flats that are happening can also be quite natural. And so it really got us thinking, and I've worked now with the Global Mangrove Watch team to try to get a bit deeper at this, that losses of coastal ecosystems might not be as simple as just coastal development. And that's what I'm going to take you through for the rest of this talk. So the scientific basis to this is that these intertidal ecosystems are exceptionally dynamic. They respond with changes to sediment inflows and water level changes and tidal changes and geomorphological changes of sediments around the coastline. And theory suggests, and as does mechanistic models, that coastal ecosystems as a whole are expected to move and maintain elevation if they're given enough room with sea level rise. So in the absence of an airport or a seawall, we expect coastal wetlands to slowly move inland with rising sea levels. And this is actually observable in a lot of places on Earth already. This image here on the right, which is associated with this paper in Nature Climate Change, shows a patch of coastal forests that are being inundated by extremely high tides, which are salt water, which kills the terrestrial vegetation and essentially turns these areas into intertidal ecosystems. And the way that this happens is incredibly complex, but if we are just observing just tidal flats or just mangroves or just salt marshes, it's actually pretty impossible to understand the full extent of these changes. And that's where we designed this new analysis to try to get at this question of where all the new coastal wetlands are being developed. This type of process carries through to our best understanding of what the world's extent of coastal wetlands is going to be in about 100 years' time. This simulation model that was published in Nature in 2018 suggested that there might even be a chance for 60% increase in coastal wetlands under some conditions. And this figure on the right here shows that under different scenarios, we might reasonably expect 60% more coastal wetlands than there are now, or all the way down to about minus 30% of where we are right now. So that range of uncertainty is nearly 100% of the extent of coastal wetlands on Earth at the moment. And it's really quite unbelievable that that sort of level of uncertainty is still carrying through our understanding of what the future of Earth's coastal wetlands might be. We also have detected, using large-scale analyses, and in this case, this is an EarthEngine based analysis published in Nature as well, that's showing that some deltas are increasing in response to increased sediment delivery. This process happens through deforestation, through removing dams and unleashing sediment to the coastal zone. And the deposition of sediment in the coastal zone means that new intertidal ecosystems can arrive in places and establish, and we can get an increase in extent of coastal ecosystems again. But at this moment, we don't really have an empirical basis to confirm this at the very large scale. There are lots of site-based analyses of coastal wetland change, but in the Google Earth Engine era, we really have an opportunity to fill this knowledge gap with information that we can glean from large-scale analyses of remote sensing data. So I set out in this project with a bunch of my collaborators to develop an intertidal monitoring system that aims to not only detect losses from things like airports and ports, but also to detect gains from increased high tides due to sea level rise, and also be able to account for transitions among types where an increase in tidal mudflats might actually allow salt marshes to eventually colonize a place and might eventually transition into mangroves as well. So with that as a sort of background to this project, we went away and tried to see if we can answer these questions using existing data sets. So here we have Global Mangrove Watch in green. We have a database developed by the WCMC in orange for salt marshes and mangroves. What we find is that mapping inconsistencies mean that this question can't really be answered using existing data sets. And this is because map error or perhaps just the linear nature of coastal ecosystems and the different forms of ecosystems worldwide, such as this shrubby mangrove here in Myanmar. What it means is that the data sets are so inconsistent that if you wanted to detect transitions or movement between these ecosystems, it's just not possible at this stage. And it really calls for an integrated analysis that aims to develop a consistent global record of how these intertidal ecosystems are changing. So in 2019, with my collaborators, Mitch Lyons here at UNSW and Tom Worthington at Cambridge University, we decided to go one step further on the mudflat project and develop a kind of global forest watch for the intertidal zone. And indeed, we've done that now. So that's what I'll talk about for the rest of this talk. Now, the basis of this new monitoring system, which allows us to track with high resolution, high accuracy, the losses and gains of salt marshes, mangroves, and tidal mudflats simultaneously, is a classic machine learning trained classification workflow, so supervised classification. We have a training data set for coastal ecosystems now. We use that to train classification models against predictor data and develop a structured monitoring product which we can deliver to end users and make freely available to scientists interested in this problem of how intertidal ecosystems are changing worldwide. To take you through step by step, our new model is based on about 60,000 observations of coastal ecosystems for a known period of time. So we anchor all of our training points to the year 2016 so that we can sample satellite data for that period and use that to train our models. We did this with about 500 hours of high resolution image interpretation, fieldwork by my collaborators all around the world, and also going through the published record of scientific papers that have published on mangroves, mudflats, or tidal flood ecosystems. And we're making this training library freely available for anyone to use in the future. So the plan here is that, you know, the basis for good conservation is being able to make nice and accurate maps. And we hope that nobody else has to do 500 hours of image interpretation to make maps of the coastal zone. And so we're going to be making this data set publicly available next year. With that, we've also got 85 predictor layers, which represent different ways of analysing satellite data that support a classifier's ability to accurately classify a pixel to each one of the coastal ecosystem types in our analysis. So we have developed a set of highly processed Landsat data that allow us to quickly run these models. So even though the classifier might take a few days to run, it's nothing compared to the amount of time it takes to build the covariates that we use in the classification. So it took about a year to develop the covariate base of this new monitoring system that we've called Global Intertidal Change. In this case, we've got about 1.1 million images in it, and we're working over a 20-year period that matches the period of global forest watch. As an example for how we use these predictor layers to inform the classification of pixels in the coastal zone to coastal ecosystem types, here's a mountain just near where I live, which shows the elevation of a pixel. And in bright red, that mountain's about 300 meters above sea level. And you know, any pixel that has a value of about 300 meters is really unlikely to be a coastal ecosystem type. So this is an informative predictor in our model. Our model is not based only on imagery. It also includes biophysical predictors such as this, mainly because of their ability to help constrain a model prediction to sort of the correct places where we know these ecosystems to occur. Another example is slope. The coastal ecosystems generally occur in very flat places. Again, this blue on this map shows a cliff, and it's really unlikely that any one of those pixels will ever be classified as a coastal ecosystem. Another layer that's informative for a classifier such as the Global Intertidal Change classification workflow. Now, I'm sure you're all aware of sort of Google's incredible ability to overcome this issue of clouds using composite metrics. So we have developed, in addition to those biophysical predictors, a whole set of Landsat-based spectral predictors, which are cloud-free and ready for analysis. And for those of you who haven't worked a lot in EarthEngine or who haven't discovered this sort of key breakthrough that using composites allow us to do, what we can do now is essentially stack all the images for a given time period. In this case, it's a 3-year time period, and choose the best pixels for our analysis. So we build cloud-free composites by filtering Landsat images and choosing the ones that are not cloudy, really. And what that allows us to do is build cloud-free image composites for the world's coastline, which really enable us to make highly accurate maps now for the entire world's coastline, which are essentially free of commission errors or omission errors caused by cloud cover. There are some costs to that, but this is really a really important thing that Google allows us to do, which is a massive breakthrough for any type of remote sensing. We do this using EarthEngine's reducers, like various reducers, but what's really neat with this, instead of choosing like the best pixel or the greenest pixel, what we do for our models is produce 60 or 70 metrics which are informative for coastal ecosystems. And this example here is, instead of using a mean or the median, which is really common, what we're actually doing is producing a variance metric for coastal water indices. So this is the standard deviation, I think. This is the standard deviation of the normalized difference water index. And what you can see here is that pixels that are intertidal, which are highlighted by sort of a bright blue along the coastline, they're the ones that are sometimes wet and sometimes dry. You know, any intertidal pixel, when an image is acquired of it, it might be underwater at high tide or fully exposed at low tide. And we interrogate the Landsat archive to find these pixels that show that type of dynamic. The ones that are sometimes wet and sometimes dry have a high value for variance when we process them in this way. And pixels that stay the same over time, they're always dry or they're always wet, have a low variance. And so this is a new predictor layer that we can use to help our classification models also make a correct classification of the coastal zone. Right. So once we've got our predictor base, 300 days of EarthEngine exports, 10 terabytes of data, and we have our training data set, more than 500 hours of time in front of high resolution imagery, we can start to think, well, let's build models in EarthEngine that can classify pixels to their coastal ecosystem type. So to do that, the first thing we do is identify pixels that we think are intertidal. So they're the ones that have a strong tidal component, such as that variance metric. And we build a map of the world's coastal wetlands this way. So this is a combined layer, which is, I mean, simply put, you are either a mangrove, a mudflat, or a saltmarsh ecosystem. You are a coastal ecosystem type. And so we first build a model that can do that. And that's this one, the occurrence of coastal ecosystems. Secondly, to sort of constrain the actual classification step, we only now work in things that have a high probability of being a coastal ecosystem. And we split that into the 3 classes that Global Intertidal Change is focused on, which is saltmarsh, mangroves, and mudflats. And with that, we develop a global map of those 3 ecosystems, as you can see here. Now, as I said in my introduction, it's almost not the extent of coastal ecosystems that matter in this case. It's the change of coastal ecosystems in response to stresses and in response to local and global scale change drivers. So we develop a 3rd step to this classification workflow, which is completely independent from the first 2 steps. It uses different training data and an entirely different set of predictor layers to then classify pixels in our time series as either lost or gained over time. So we use the extent layers to flag pixels where it looks like change might have happened, where coastal wetland might have been gained or might have been lost. We go into them and then we run another classifier that goes to the pixels and uses predictors to estimate whether or not those changes have actually occurred. And in this case, the target map classes are loss, gain, or no change. Now, that might sound complex, but it really isn't. I'll take you through it so it's hopefully easy to understand. Here's a patch of coastal wetlands in Myanmar, made up mainly of mudflats, which you can see here in brown. mangroves, which you can see fringing the coastline. First thing we do is we develop that first classifier, and this is a random forest probability output showing the likely distribution of coastal wetlands. And we make a classified map of coastal wetlands for the whole world like this, which here you can see in grey. Then we go into that and we go into those pixels and we say, well, what sort of coastal wetland type are you? Are you saltmarsh, mangrove, or mudflat? And that's when this classifier will make that decision and deliver a global map of the extent of each of these three ecosystems. And then the last thing we do, which I'll show you with another example, is process all of this to understand gain in a way that's highly structured and will form the final product that we'll publish. So starting with this coastal wetland distribution map, here is Singapore, just for this presentation. Here's Singapore, here's Peninsular Malaysia, and in brown you can see the extent of any one of the three coastal ecosystems that we're focused on in this analysis. Our change classifier, which is the third classifier, dives into our archive of maps and then classifies the likelihood of being a gain, which is shown in blue, or being a loss over a 20-year period, which is shown in red. So all these patches in red suggest that coastal ecosystems were there in the past but aren't there now. And all these patches of blue suggest there's something new there that wasn't in the past. So we can go into each one of those patches. Here's a patch of gain in Peninsular Malaysia. And we can say, well, what type of gain are you? What new ecosystem type are you that you weren't here in the year 2000? And here in yellow, we have mudflat and mangrove in green. So you can go to this place in Peninsular Malaysia and go and stand in mangroves that are less than 20 years old, or stand on a mudflat that's less than 20 years old as well. Using our time series of maps, we can then allocate each of these new pixels to the year that they first showed up in our record, so that we've got a change year layer as well. And in this case, you can see this slow southern migration of a new patch of coastal wetlands on the Earth's surface, with yellow being the most recently deposited and purple sort of showing up in the year 2001, I think it is, or 2004. So that's the sort of information we've got in this data set. We do the exact same thing with loss. So we can go to a loss patch and we can identify the type of loss that occurred. This is the ecosystem that was in the year 2000. The opposite of that is gain, is what is it now? For loss, we say, what was it before it was lost? And then we can work out the year that loss has occurred. And so here we can cross-reference that with information, say from the news or through fieldwork, to confirm that this patch of mangroves, in this case, was lost in the year, in the time step of our analysis between 2010 and 2013. And indeed, it was a new port launched in 2012. So that's the basis of this new data set. Some other examples of our ability to detect these changes are sort of engineered changes, such as the moving of outflows from major rivers. In this case, the Yellow River in China had a channel diversion in the late 90s. And what happened then was the erosion of tidal mudflats on the southern coastline and the deposition of new tidal mudflats where the new diversion entered the ocean. Similarly, we can detect ecosystem gains through restoration. This one here is in the UK, just near London, and it's a new patch of salt marshes that was developed through this multi-billion-dollar ecosystem restoration program to take farmlands and turn them back into coastal ecosystems. So we can detect these changes from space now, and our data set's able to detect gains of coastal wetlands by restoration all around the world. And then our ability to sort of get the year right in the data set is also able to be tested against some known geological events. In this case, this is one of the largest earthquakes recorded in the last 100 years. I think the second largest earthquake in the last 100 years. The 2004 earthquake that sort of devastated much of Southeast Asia in the Nicobar Islands resulted in a nearly 2-metre subsidence event, in that the coastal zone dropped by 2 metres with this massive tectonic change, And what happened then was that all of the mangroves that used to be in the intertidal zone were drowned and died off. And you can see that here. We detect that there's a loss. And when we dive into the high resolution imagery, we can see this dying off of mangroves, this brown here, and eventual complete drowning of where the mangroves used to be. So we detect that loss with fairly high accuracy. So what does all this mean on the global scale? Well, the interesting thing, I think, is that it shows that losses and gains of coastal ecosystems are fairly commonplace, and they're focused in a couple of places in the world, mainly large deltaic regions, so places where there are huge sediment inputs and there are sort of unstable coastal zones caused by this massive sediment input. We also detect like really large losses in Myanmar, Southeast Asia mainly, and China as well. So East Asia and Southeast Asia as being a hotspot of loss, as well as those deltas in the Mississippi and in South America and Africa as well, such as the Niger Delta. So when we look at gains, we see that they really happen in places where deltas are. This is places where there's new sediment for the system, and that sediment gets deposited and new coastal wetlands are able to form. And then lastly, transitions also show this similar pattern as being in these dynamic coastal environments, which are deltas. So this is where a mangrove or a mudflat or a tidal flat has not actually been lost from coastal wetlands. They've just changed from a mudflat into a salt marsh, or from a mangrove into a salt marsh, or a salt marsh into a mangrove. That's what we mean by transition. So it kind of shows that coastal wetlands are massively dynamic, and we can detect that change now at the global scale. So there's just some headline figures from the analysis so far. Almost all of the losses, like net losses of mangroves globally net losses of coastal wetlands globally were of mangroves caused by deforestation. And you can see that in this bar plot, where the green is much larger on the lower side of zero, meaning it's the extent of losses, than it is on this positive side of zero, which is the extent of gains. Interestingly, salt marshes and tidal flats were relatively stable in this analysis, suggesting that even if mangroves are deforested, that might open up sediments, which then get delivered somewhere else, and a new coastal ecosystem can eventually form on those layers, on those new sediments that are deposited. Quite alarmingly, though, that nearly 70% of the net losses occurred just in Indonesia, China, and Myanmar. These are the global hotspots of coastal wetland loss. And any efforts for conservation should be directed here as quickly as possible. And indeed, they already are in lots of cases. So yeah, with that, just some final steps. We're writing this up now. It's going to get submitted fairly soon. And we'll be delivering the data set, the code, the training data as open access products. We've taken the training set and actually worked with a bunch of other global mapping projects to incorporate their data as well into this publicly available coastal machine learning training set. So we're working with Alan Coral Atlas and the Global Mangrove Watch and the original Mudflat project, as well as Tsinghua University's global higher resolution land cover project. All of that data is coming into Coast Train, which we call the training set, and that's going to be published for people like you to go and make maps of mangroves and salt marshes and corals and coastal ecosystems all around the world. We're making maps of salt marshes now in places where there are no consistent data, and there's obviously a bunch of downstream analyses that are possible from a data set like this. So we're working on that, and always keen to work with people who'd like to use our data, and happy to do that. So feel free to get in touch with me if you're interested in that. Now, as an EarthEngine conference today, I thought it's nice for me to just sort of give some comments on EarthEngine, having worked in it for nearly 10 years. Most importantly, none of the work we've done in EarthEngine over the years really could have been done in R or really any other high performance computing environment, except for maybe what Tsinghua have been able to achieve with theirs. And so what we've done is had massive trade-offs in the way we've done things so that it works in EarthEngine. And I would say just do it. Don't don't wait too long to take something that you know might work on a certain algorithm in a different system. I would say adapt to it. It's something that we found to be really fruitful. Be willing to change the way you do things so that you can use EarthEngine, because EarthEngine allows you to do a lot of things that are really difficult otherwise. When I started in EarthEngine and when we were doing the EarthEngine Research Awards projects, there weren't any best practices or debugging guides. And so we did a lot of trial and error, and I worked really tightly with Nick and the other developers to do these types of analyses. Well, now I think you can learn from all of that and follow these best practices and debugging guides. They can save you an enormous amount of time, and there are better ways of doing things in EarthEngine than some other ways, even though they might both be possible. When you scale up to the global scale, it generally exposes the limitations of EarthEngine. And so using the guidance provided by the Google developer team sort of helps you work at what's possible with EarthEngine at large scales. All of the information of the thousands of users of EarthEngine now is also incredibly important as well. So I can't recommend enough just trying to learn from others rather than just staying with the guidelines. Get on Stack Overflow and the developer forum and learn from people who have had trouble. And the chances are someone's done something that you're trying to do, and now it's time to be using that knowledge base. I know from working with the Google team for a couple of years now that they really appreciate any bugs, any bug reports. So if something's acting strangely, just to let them know, and they work really quickly to solve anything. And we've found a lot of bugs in our projects, and that's been able to end up with meaningful changes to EarthEngine. Same with feature requests and data requests. The EarthEngine team really appreciate that. So see if you can make EarthEngine better and get one of your feature requests adopted. And then lastly, this is just more on a personal note. I think using EarthEngine for good and for conservation means that we should really be trying to make anything we do available to other people in the hope that it promotes conservation. And so I really work on reproducible and open access data and analyses, mainly because I just hope that some of the work that we can do in EarthEngine ends up conserving ecosystems where they might otherwise not be. And so with that, I'll finish my talk and just say thanks to an enormous team that have helped me over the years. Thanks to the IUCN who have helped constrain some of my thinking about how the world's ecosystems are changing. The Australian Research Council funded this latest project. And lastly, if anyone's interested in doing a PhD, come over to JCU in Townsville. I've got a couple of projects I'd love to talk to you about. So get in touch on my email. Thanks, everyone.